Welcome to the college algebra application problem dealing with the human cannonball. The reason we use this human cannonball project is because it gives a good illustration of how you can use quadratics to model things that actually occur in everyday life. And as you'll see with the human cannonball, knowing the correct quadratic formula to determine where you're going to end up with after you get shot out of the cannon could be a positive thing to, maybe help you do something like hit the net. But what we can do is we can use parabolas for modeling the trajectory. Any kind of projectile trajectory will follow a parabolic path. In other words, it's a parabola. By projectile, we mean something that is thrown, pushed, shoved, or otherwise hurled into the air, but not moving under its own power. So if you know a few pieces of information about it, using a parabola, you can calculate the path, and that's what we're going to do with the human cannonball in these following slides. So you can see from this slide, this is a time-lapse slide, shows the position of the human cannonball over a period of time as after he shot out of the cannon. So there it goes. Can you see the parabola? Well, I want you to think not only about the parabola, but I want you to think about the transformations and shifts in the parabola. Remember, we did some transformations and shifts, things that would shift the shapes, the graphs upwards, downwards, left, right, maybe reflected about the y-axis or the x-axis. And that's the kind of things that we're going to be doing when we look at the human cannonball. Now, if we overlay a grid on a picture, we can see how much like a parabola the trajectory is, and we can also determine where the zeros and the vertex are located. You can see the zeros are going to be at the base of the cannon where the human cannonball is shot off, as well as at the landing net where hopefully the human cannonball is going to land after flying through the air. You can also see the vertex, which is the highest point of the human cannonball's flight. So how can we model this? Well, first let's just start out with the graph of a parabola y equals x squared. This is the general parabola, nothing special. We can make the graph, and we've done this using an xy table or whatever method you prefer, and you get something that looks like this. Now this doesn't look much like the path of the human cannonball, does it? I mean, he would have to go down and come back up. It's just not quite what we're looking for. So let's start thinking about something else. Let's think of a piecewise function. Because let's face it, once the human cannonball leaves the cannon, he's leaving 0, and he's going for a certain distance. And we're going to say 180 because in the flight that we looked at, he flew through the air 180 feet. So we're just going to take a piece of the parabola y equals x squared and just graph it for x equals 0 through x equals 180. And when we graph it, we get something that looks roughly like this. I apologize for my curve not being perfect, but it's very difficult to come up with a perfect parabola through the software that I was using. But you can see that, hey, maybe this might have something going, only it's just going up. It's not going down anywhere. So if this was the true trajectory, the human cannonball would never land. He'd go on forever and maybe fly out in outer space or somewhere. Probably not the most effective model at this point. So how can we change the graph to model the human cannonball? Well, we know it's roughly going to be a parabolic shape, but how do we make our parabola at least look like the right shape, where he's going up from the cannon and then going back down? Well, what happens if you decide to flip or reflect the parabola about the horizontal axis? How do you do it? Well, you simply multiply the x squared by a negative. So that's what I want you to do here. I want you to go ahead and graph the same parabola y equals x squared, only I want it to be negative of x squared. So you'll see that you end up with something that looks like this. Well, this looks reasonably good for the second half of the flight, but it's not going to work for going up in the air and coming back down. Have we modeled the trajectory? No. It's about half of the graph, but we still don't have the correct overall shape. However, if the cannon was horizontal and we were shooting the human cannonball down into a big ravine somewhere, this would be roughly the general shape that the trajectory would take. So we're going to have to get a little bit more information before we can get the correct trajectory. Now when we look at the flight path of the human cannonball, you can see that there's very much a parabolic trajectory, but let's look at what are the key points that we need to know. Well, off at a first glance, it's pretty easy to see just about 3 key points. We've got a couple of zeros, one where the human cannonball leaves the cannon, or actually where his feet are when he's in the cannon. Another 0 where he hits the net when he lands. And we also have the vertex. Now these pieces of information are key to identifying and modeling the actual parabola. So how can we move the parabola to match the human cannonball? Well, we've got a couple of shifts that we're going to have to do. One shift is we need to move the vertex vertically. Because the vertex right now is at 0, 0, or at the origin, we need to shift the parabola upwards by 70 feet, or by just 70 on our graph. So we do need to go up. So how do we shift a graph upward? Well, remember, we shift vertically by either adding or subtracting a value from the function itself. So our function is x squared. To shift up, we would need to add 70 to it, so we would end up with the new expression, x squared plus 70. That would shift it up. What about the horizontal shift? How much do we have to shift our vertex either to the left or to the right? Well, since the total trajectory is 180 feet, the vertex would have to be right in the middle, or at 90 feet. Then we have to figure out which direction does it shift. Well, 90 feet to the right. It's not going to go backwards, because then it would be some kind of strange flight pattern to turn around and go backwards. So to follow our parabola, it has to shift to the right. So how do you get it to shift to the right? Well, to shift left or right with any graph, you're either going to have to add or subtract a value within the function itself. So to move it to the right, you're always going to have to subtract. So we're going to subtract 90 within the x squared term. In other words, we'll have x minus 90 squared. So basically, what have we got? We've got a new function that can be described, or a new model that can be described as x minus 90 quantity squared plus 70, which would allow it to shift up 70 and to the right 90. So now we're going to take our general parabola, y equals negative x squared, and we're going to have a vertical shift to 70, so we raise it up, and a horizontal shift of 90, which means you're going to spread it off, you're going to scoot it over to the right about 90. Did that make the graph of the model follow the flight path? Well, not really. It's still too skinny, isn't it? Because if you think about it, if you go back to the graph, you can see that this is going to be a problem, because the 0 is not actually where the cannon is, nor is it where the net is. So this could be problematic for the poor guy flying through the air. He's going to have to take off from underground, and he's going to end up hitting the ground somewhere away from the net. So how can we modify the parabola to more closely fit the data? Well, we have to look at our shrinking and stretching horizontally and vertically. And basically the best way to do that is to use the general shape of a parabola, y equals a times x minus h squared plus k. So how can we use this to our advantage to make it fit more correctly? Well, one thing to remember is it is possible to find the equation of a line using y equals mx plus b, and we did this by substituting in the slope, and we substituted in the points x and y, and we could find b that way, right? That's how we find the y-intercept. Well, we can use the general shape of a parabola and do something very similar to that. We know the vertex from our graph. What was our vertex? Remember, it was over 90 up 70, so it's going to be, the vertex will occur at 90, 70. We also know the ordered pairs on a total of 3 points. What are the points in those coordinates? Well, you've of course got the starting point 0, 0. We already talked about the vertex at 90, 70, and we have our last zero, our landing point, at 180, 0. So this is great. We've got some new information. Well, how do we use it? Well, what we're going to do is we're going to substitute the vertex and a point in the equation for a parabola, remembering that h and k are the vertex coordinates. Once we do that, we will be down to a single variable, which is a. So we're going to substitute in an x, a y, an h, and a k, and be able to find a. And remember what a does to your parabola. It is when you multiply times the original function. If you multiply by a number bigger than 1, the absolute value is bigger than 1, it's going to stretch it. If you multiply by a number that is between 0 and 1, the absolute value between 0 and 1, it's going to squash it down and basically spread it out. So let's plug everything in and see what we have. First, I'm going to plug in my vertex, so I have y equals a times x minus 90 squared plus 70. Then I'm going to plug in one of my points, and I'm going to use the point 0, 0 simply because it makes the math easier. I could use the 0, 180 and get, or the 180, 0 and get the exact same results. So when I plug in the 0 for x and the 0 for y, I already have my h and my k in there. You notice the only variable left is a. So when I solve this equation for a, I find out that a equals negative 70 over 8100, and you can see the decimal equivalent here. Now we're going to graph the new parabola. We might have to adjust the scale to fit the graph, but really, as long as you use one tick mark equals 10, it works pretty well. So here is our new parabola. Now this is looking a lot more like the human cannonball, isn't it? In fact, if you were to print this graph off and a picture of the human cannonball at the same scale, that the parabola fits very nicely along the trajectory of the human cannonball. So you can see the parabola that we created actually models the human cannonball flight very nicely, which would be a nice thing to know if you happen to be the guy being shot out of the cannon, because that way you know with reasonable confidence exactly where you're going to land. That way you don't miss the net. Missing the net could be a problem. So, how did your parabola compare to the actual trajectory of the human cannonball? Well, based on what I've seen here, it looks like it fits it exactly, which is a wonderful thing. And I really didn't see any differences that occur. Now, on some other models, they may not fit quite as perfectly as this one does. For example, if you're modeling bullets, bullets actually lose momentum over time and they start dropping off a little bit more quickly, so they don't follow the trajectory perfectly along the entire flight path. But for the short distance, it really does. So this concludes this mini lecture on the human cannonball, and I hope it is very helpful to you.